Up next, the last part of this unit that we are covering is optimization. And what is optimization? I'm going to give you an easy example, and then I'll give you a little hard example. So a very simple kind of optimization is going to be a problem like this. It says find two positive numbers whose sum is 30 and whose product is a maximum, right? I'm trying to find two numbers that add up to 30 that multiply to the biggest possible number. So how could you do that? We see that we're looking for a maximum, and we already know how to find a maximum, right? You derive it. You're trying to find the absolute maximum. So all we have to do is turn this problem here into a function that we could derive and then plug in to find the absolute maximum, right? So we have two positive numbers whose sum add up to 30, and we're finding the product. So we know that x plus y, these are our two numbers, equal 30, and we're trying to find xy. We're trying to find the maximum volume of xy. So this down here is the function that we're maximizing, right? We're maximizing xy, the product. If we have two variables here, it's way harder to do this. So what we have to try to do is make it just one variable. So if we know that x plus y is 30, we know that y equals 30 minus x, right? Because all this is doing is moving the x over to the other side. So we could rewrite our product function as x times 30 minus x, right? Because y equals 30 minus x. So if we're just replacing the y with 30 minus x. Now we can write this as 30x minus x squared. And now this is the function that we're trying to maximize. So if this is our f of x, and we're trying to find the absolute maximum, we're going to have to find critical points, right? So we'll look at our f prime of x, which is 30 minus 2. And if we set this equal to 0, we get 30 minus 2x equals 0. We'll move our 2x over. We'll get 30 equals 2x, or x equals 15. So we know that our x value is 15. If we want to plug it back into our original equation to find the y, you get 15 plus y equals 30, or just y also equals 15, right? So our two positive numbers here are going to be 15 and 15, because this gives you the absolute maximum product that you can get out of this function. This one would not have been too hard to solve without calculus, but this is just an example of how it works at a simple level, right? You want to make it into a function and maximize it. So let's look at a more complicated example where we have to use some calculus. Okay, so this type of problem they love using. I don't know why. When I was studying for the AP test last year, and on the AP test you just get this question so much, right? So this one says, suppose you are constructing a rectangular fence along your property using a river as one side and wood for the other three sides. Given 100 feet of wood, determine the dimensions that would create a fence with a maximum area. So first thing we got to do is translate this, find out what you're saying. We want to make a rectangular fence around your property, right? And you're using a river as one side and wood for the other three sides. So there's a river right here, and you want to make a rectangular fence using the river as one of the sides. So you only have to make three sides, right? You have 100 feet of wood, and you're trying to determine the length and width that would give you the maximum area. So again, we're trying to find the absolute maximum. So we have to turn this into a function that we could derive, right? So area equals length times width. This is the function that we're working with. And you know that 2 length plus 1 width equals 100, because you have 100 feet of wood and you have 2 lengths and you have 1 width, right? Or you could have 2 widths and 1 length. It doesn't matter. It's the same thing. You also know that if you move this 2L over, you get W equals, or the width equals 100 minus 2 length. All you're doing is moving the 2 over. So now that you have that, you can replace this W with this 100 minus 2 length, because they're equivalent, right? So then that leaves you with the function area equals length times 100 minus 2 length. Or you could distribute that out. You get 100L minus 2L squared. And this is going to be the f of x function that you use for this problem. So now that we have the function that we're trying to maximize, we're going to do the same thing. We're going to derive it. We're going to get f prime of x equals 100 minus 4L. Now if we set this equal to 0 to get our critical point, we'll move the 4L over, and we'll get 100 equals 4L. We'll divide both sides by 4, and you'll get 25 equals L. So the length of one side is L. And then if you remember, our original function, we had 2L plus W equals 100, right? Because we have 2 L's, and we have 1 W, and we have 100 feet of wood. So now that we know that L is 25, we have 2 times 25 plus W equals 100, or 50 plus W equals 100, or W equals 50. So over here on the right, we know that we'll make a 25 by 50 foot fence. And our area is, we just multiply 25 and 50, and we'll get 1,250 feet squared. So again, optimization problems, you're just trying to turn it into a function that you could derive. That's the one thing you have to do. You have to find a function that you could derive, try to get just one variable, and then derive it, set it to 0, and find the absolute maximum like we have been doing. So that's it for optimization, and that's it for Unit 5. So we're moving on to Unit 6.